So whenever we have a speech waveform, we can subject to it various digital procedures. And well, we may want to establish some fundamental characteristics, and this is what we call speech analysis. These characteristics are many. We may want to know the speaker, for example, who it was, or the nature of the speaker. Was it a child? Was it a man? Was it a woman? We may want to know the method of production. How was this sound produced? We may wish to know the characteristics of the environment in which the sound was made, plus any other interesting information, because current research has shown that there's much more hidden in speech than we previously knew. So because of this, it also enables the development of better algorithms for processing speech and also better speech acquisition hardware. By performing analysis and knowing our limitations, we are prompted to develop better techniques to acquire it and to process it. Okay? Necessity is the mother of invention. So whenever we are analyzing speech, there are three basic parameters that we are looking for. At the basic level, this is what we call the short time energy, what we call the short time zero crossing count, or you can call it the zero cross count, and also the pitch period, which is related to the fundamental frequency. When we say short time, it means that in a long frame of audio, we are just getting a small chunk, which is about maybe 10 to 20 milliseconds long, and we analyze it at a time. 10 to 20 milliseconds is not an arbitrary value. This is roughly the order of magnitude that it takes the vocal cords to vibrate. Okay, it's probably around 50 to 100 hertz. So this is why we select such a time. We are going to look at each of these independently. For example, this is the waveform of the word imperative. You'll notice that at the beginning of the waveform, we have a spike. The waveform itself, we have an average value of about 0.6, but then at the beginning we have a spike, and at the end we also have a small spike. These are called start and end points, and usually we do not include them in our speech analysis because, well, because they are outliers. For example, the start point can be created by the recording device at the beginning of recording. Maybe if I press a button, there is a small outlier that is caused by the button press before we start speaking into the ADC. So usually we trim the start and end points, and using a tool like MATLAB, we can zoom in on a particular time frame, maybe at 1.5 seconds, and we even have a better view of the nature of the waveform. Now, the short-time energy, what we do is we divide a speech sample into n frames, and then each frame we compute the sum of the squares of the sample points. The equation is down there, okay? And well, we use a window function. I'm sure you've learned what window functions are. But the reason why we use the sum of the squares, we could have just used the sum, but the problem is when you're speaking, we have vibrations, we have compression and we have rarefaction. So that the compression causes an electrical voltage of an opposite sign as compared to the rarefaction. So in a sample speech frame, you'll find that you have positive values and negative values. This is at the software level. Once you've acquired it and saved it into an array, we have an average, then we have positive values and negative values. There may all be positive values if, let's say, we have some DC content, okay? And the speech signal, the mean is not zero. But usually, before we perform the short-time before we calculate the short-time energy, we remove the DC content so that the mean value of the speech frame is zero, and then we get the sums of the squares. So if you just calculate the sum, the negative values would cancel out the positive values. But if you get the sum of the squares, then we have positive values only, and that shows energy. It's just like voltage. Negative 12 volts and positive 12 volts, they are the same magnitude. Okay? Negative 240 volts can shock you. Positive 240 volts can shock you in the same manner. So this is the same concept that we apply here. Okay? To get, when we're summing them up, we first square all of them so that we make all the values positive, and then we calculate the energy. So the choice of the window that you use has a great impact on this calculation of the short-term energy. Okay, basically we do not want the number of samples to be too many, and we also don't want them to be too few. Okay, if the window is too long, the energy will change very little with time, as you're going to see in the next slide. So we need the length to be short enough to show the rapid changes of the amplitude with time. If the window is too small, then the energy will fluctuate very rapidly. Okay? And it will show the specific details of the waveform. And usually we are just looking for energy. We don't want the specific details. The specific details are in the original signal from which we are computing the energy. Okay? So if you're performing an analysis technique that requires specific details, then it's better you probably leave it in the original. It's better you probably leave it in the original form. But energy is energy. We want to know the intensity, okay, of how much is contained in a particular time frame. Okay, was the person speaking with a low volume? Was the person speaking with a high volume? There is no universally accepted length for the number of samples that you should take inside this window. However, for practical purposes, we do not want the frame to be, we want the frame to be between 10 and 20 milliseconds. Okay, let us look at an example. For example, this is a waveform of 6. Okay, we haven't yet calculated the short time energy in this particular waveform. This is just the waveform. When I say the word 6, this is how the waveform perform. Here I perform the short time energy calculation. It's a pity I didn't include the sample. I didn't include the sample number. I think it's 50. We are going to look at another example where I have written the sample number on the slide itself. Okay, but as you can see, the two separate parts, the two parts of the waveform, the previous waveform that we saw, the two separate parts, they are still visible here, but we have lost some detail. Okay, and it is easy to, each of those spikes that you see represents a particular amount of energy that was contained in the original signal. Okay, so this shows you, for example, that the second part of the waveform contains more energy than the first part. Okay, this is MATLAB code. Please run it, okay, so that you can get an idea of what we're speaking about. In particular, you should note that we are removing the DC content on line number 5, and then we are also normalizing. Normalizing means that we make the maximum value to be equal to 1. When you're recording, usually the maximum value is some decimal. Okay. Now the sampling frequency, in my case, the sampling frequency was 44.1 kilohertz. That means if I want a frame of 10 milliseconds long, I have to get 441 samples. Okay, and that is precisely what I've done by setting P is equal to 441, and then I come and I calculate where you see the for loop. That is where I'm calculating the actual short time energy. Notice how I am squaring. Every element. Okay, every element I'm squaring it and adding it to the total sum, and then after that I compute the short time energy at the case index. Then I add on to the index. So basically, you get 441 samples, and from those 441 samples, you get one energy value, okay, by performing the sum of squares. Then you get the next 441 samples, and you also add them to the k plus 1 index. Okay? So the ek is going to represent the short time energy values that you have obtained from the individual sample points. And those are the waveforms that we have been seeing in the previous slide. So this is using P is equal to 50. I think this is still the waveform of 6. Yes, I think this is still the waveform of 6. Here I am using P is equal to 50. That means it's short. As you can see, there's a lot of detail in the resulting graph. Here I'm using P is equal to 1,500. As you can see, I've lost too much detail. Okay, so ideally I want to choose a value of P which is roughly in between. So the short time zero crossing count is the number of times that a signal crosses the time axis. So you can already see that it is directly related to the frequency. If we have a high ZCC, that means the signal has a high frequency. Now the signal must have a zero DC content if we are to calculate the zero crossing count. Okay, what zero DC content? It's there in the previous MATLAB example that I've shown you. But what we do if you have an array of values and you want to remove the DC content from the array, you get the average of that array, and then the average of all the elements in the array, and then you subtract that average from each individual element. For example, if you have an array with 3 elements, 2, 3, and 5, okay? If you are to plot these, you'll see that all of them are above the x-axis. 2 is above the x-axis, the positive value, 3 is above the x-axis, and 5 is above the x-axis. Now, the average of these, 2 plus 3 is 5, 5 plus 5 is 10, 10 divided by 3 is 3.3. So the average of these is 3.3. So we come back and we subtract 3.3 from every individual element. So that means the values now will be negative 1.3, negative 0.3, and 1.7, okay? So you realize that you have now 2 values which are below the x-axis and 1 value which is above the x-axis. And if you're to sum up all these values, the answer should be 0. There's just a small rounding error, of course. I have negative 1.3 plus negative 0.3, that is negative 1.6. If you add 1.7, you get 0.1. But ideally, if we had retained the decimals, you should get 0. That is what we mean by having zero DC. Having 0 DC content means that the average value is 0. That means that the signal is uniformly distributed. The energy below the time axis is equal to the energy above is equal to the one above the time axis. Okay, that is the formula for the 0 crossing count. You get the sign. That function is the signium function, the signaling function. And if a point is above the time axis, we get positive 1. It returns positive 1, and it is below the x-axis, we return negative 1. For example, if sk has a value of 2, then the sign of sk is positive 1. If sk has a value of negative 1, then the sign of sk is negative 1. Or if sk has a value of negative 3, then the sign is negative 1. So it's always either positive 1 or negative 1, depending on where you are, above or below the time axis. Okay? You can simply apply, and then after that we get the modulus. You can apply this to a sample array. For example, if you have 2, this is an assignment. If you have 2, an array, these are the elements of the array, I'm reading them out. 2, negative 3, 4, 5, negative 6. What you'll do is you'll first remove the DC content. After removing the DC content, you find the ZCC, the 0 crossing count, using that function. Then you plot these points, okay, on the time axis and confirm that the ZCC is equal to the number of times this signal actually crosses the time axis. Okay, you'll have to combine these signals. You'll have to combine the data points using lines so that you get a waveform out of them. Okay, this is the same waveform of 6. This is the short time 0 crossing count. As you can see, the areas where the actual word 6 is, we have high values of the 0 crossing count. I'm taking p is equal to 441. Okay, ZCC is very useful in differentiating between voiced and unvoiced sounds. Okay, unvoiced sounds have high frequencies, like the fricatives, and they have high ZCCs. And voiced sounds have low ZCCs. For example, this is the 0 crossing, the short time 0 crossing count for the sound of O is a voiced sound. Okay, so you can see that we are averaging around 30. Okay, we are averaging around 30. But this is the one for which is an unvoiced sound, and as you can see, the 0 crossing count average is about 160. Okay, writing the MATLAB code for that should not be very complicated. So, what are the uses of energy and the 0 crossing count? They are used for automated start and endpoint detection. Okay, ignoring, of course, background noise and what we call intra intra-1 silence is if you saw, for example, the waveform imperative and 6, they have a small silence in between. That is what we mean by intra-word silence. Okay? They are used in voice and unvoiced speech detection. If we have a high zero crossing count and a low short-term energy, usually that is unvoiced speech. Unvoiced speech has small energies. Voice speech, on the other hand, has high energies but a low zero crossing count. This is just the waveform for 10. Very compact. There's no intra-1 silence there. That is the short-term energy for 10. Now, pitch period estimation. Well, pitch period is the inverse of the fundamental frequency. Okay? Now, when you zoom in into a particular signal, for example, this shows you just 5,000 samples. You see there is some nature of periodicity. Okay? We call this quasi-periodic. Quasi-periodic means well, it is pseudo-periodic. Okay? We have a periodic nature in it. Okay? Now, this I think is for the recording of the word 10. I just zoomed into a particular location which had some voice speech. Now, how do we get the period? Okay, we can use the raw analysis. For example, in the previous slide, we just look out for the periodicity. We look for the troughs or the crests. We get the time interval between those, and we find the inverse, and we say, hey, that is the what? That is the pitch. Well, that would be the pitch period, the time period between them, and then we can get the fundamental frequency by using the inverse. Okay. But there are usually two techniques that work best. The first is the short-time autocorrelation, and then the second is an average magnitude difference method. The second is left to you for research. Okay. Now, how do we use autocorrelation? Okay. In MATLAB, there's a function called xcore. Basically, you get a smaller part of you first extract maybe 5,000 samples from the larger signal. You extract maybe 5,000 samples which you're going to use to get the autocorrelation. Then from those 5,000 samples, you extract a smaller sample which you're going to perform a cross correlation with the larger sample. So we have two samples that we get out. One sample from the big one, let's say about 5,000 sample points. Then another sample, let's say maybe about 500 sample points. Okay, from the 5,000 samples, and then we perform a cross correlation. Okay, you can get something like that. Okay, you get something like this, which looks much more beautiful than the original sample. A cross correlation, really what happens with a cross correlation is that everywhere where you find similarity, the resultant cross correlation array gets a peak. That is how we identify similar. That is how we can know whether a small part of an array is contained in a larger part of an array. We perform a cross correlation, and where we get a maximum, that is the index in the larger array where we found the smaller array, or something that looks very close to the smaller array. So it is now easier to estimate the pitch period from this. As you can see, we have the periodicity is even much better. Okay, so this is the resultant. This is the resultant that we get if we zoom into two troughs. As you can see, these are about 354 samples. We have a first trough at around 447, the second trough at around 801. I was recording at 44.1 kilohertz. That means those are about 300. We have 354.1 samples and yet we are 44,100 samples per second. So that means those troughs were recorded within a period of 0.008 seconds, and you can calculate the fundamental frequency. It is not visible there, but it should come to around 125 hertz. These are the average magnitude difference methods, and I am leaving this to you. Okay, how is it used in analysis? In a way, it is the reverse of the autocorrelation function. Okay? exercise. If you have time, you can simply perform that exercise. Record the word 9 and perform an STE and the ZCC.